We'll start this last video of this lecture by coming back to the argument that we saw from the beginning of the lecture that showed that Z was a PID and also that f bracket x was a PID. So the main point here is that Euclidean domains are PIDs. Here's proposition 1 of section 8.1 of Dummett and Foote, page 273. Let's say that R is a Euclidean domain. Then every ideal of R is principal. So R is a PID. More than that, we can say that an ideal is principal by describing a generator for it. More precisely, let I be a non-zero ideal of R. Then I is equal to the ideal generated by D, where D is any non-zero element of I of minimal norm. And the proof is just going to be just like what we saw for Z and for f bracket x. So if I is a trivial ideal, then it is the ideal generated by 0, and there's nothing to do, and we're done. So let's suppose that I is a non-zero ideal of R. And let's pick D in I to be a non-zero element of I of minimal norm. Clearly, the ideal generated by D is contained in I. And our job is now to show that inclusion holds the other way, that we pick an arbitrary element of I, and it's in the ideal generated by D. So let's pick A in I. By the division algorithm, which we have because we're in a Euclidean domain, we can write A equals Q times D plus R, where either R is 0 or the norm of R is less than the norm of D. Well, now A is in I and Q times D is in I, so A minus QD, that's R, that's also in I. But now we assumed that D was a non-zero element of I of minimal norm, and R is some element in I, and the norm of R is less than the norm of D. So that means R cannot be a non-zero element. So R is 0 by the minimality of the norm of D. So what does that mean? That means that A equals Q times D plus 0. A equals Q times D. So A is in the ideal generated by D. So now A was just an arbitrary element of I. That means the whole ideal I is contained in the ideal generated by D. So we have inclusion the other way, and I is equal to the principal ideal generated by D. OK, this should feel very similar. This is just like what we saw for Z and for f bracket x. So what is this good for? One thing this is good for is we had a way to see that a ring was a Euclidean domain, which is you come up with the right norm, and then you prove that you have this division algorithm. This proposition gives us a way to show that an integral domain is not a Euclidean domain, which is a Euclidean domain has to be a PID. So if you have an integral domain that's not a PID, it is not a Euclidean domain. So how are we going to show that something is not a Euclidean domain? Show it is not a PID. So our first example is last quarter when we talked about ideals and what it means to be the ideal generated by a subset. We saw that the ideal generated by 2 and x is an ideal in Z bracket x. It's a proper ideal that is not a principal ideal. So that means that Z bracket x has an ideal that's not principal. So it's not a principal ideal domain. And what does that mean? It's not a principal ideal domain. So it's definitely not a Euclidean domain because every Euclidean domain is a PID. So I'm going to pause and erase. And the last thing that I'll do is give another example where we show that a ring is not a Euclidean domain by showing that it's not a PID, by showing that there is one particular ideal that is not a principal ideal. Let's consider our next example. Let's say that R is Z adjoint square root of minus 5. And remember, we have this norm function on Z adjoint square root of minus 5 that comes from the field norm. So that is norm of A plus B square root of minus 5 is A squared plus 5B squared. So this is this field norm, or this norm on this ring. I'm not at all saying that this ring is going to be a Euclidean domain with this norm. It isn't. In fact, what we're trying to show is that this ring is not a Euclidean domain, but we still have this norm function on it that, remember, has certain nice properties, like it's a multiplicative function. All right, let's consider this ideal generated by 3 and 2 plus square root of negative 5. the whole idea here is we're going to show that, okay, when you have an ideal generated by two things, sometimes it's a little hard to see whether or not it is in fact the whole ring. So first we're going to see that it is a proper ideal, and then we're going to show that it's not a principal ideal. What will that tell us? That'll say that we have an ideal that is not principal, so R is not a PID, and by the result that we proved at the beginning of this video, that means that R is not a Euclidean domain. All right, let's do this first part. Let's argue by contradiction. Let's suppose that I was a proper ideal. Sorry, was not a proper ideal, that I was equal to the whole ring. That means that you could write anything in R as something times 3 plus something times 2 plus square root of negative 5. So what would that mean? In particular, if you could write everything that way, you could write 1 that way. So there would be gamma and delta in z adjoint square root of negative 5 in R, with 3 gamma plus 2 plus square root of negative 5 delta equals 1. Let's multiply both sides of this equation by 2 minus square root of minus 5. Why might you do that? Well, that is this conjugate of 2 plus square root of negative 5. When you multiply 2 plus square root of minus 5 and 2 minus square root of minus 5 together, simplifies. Good things happen. So what do we get? We get 3 times 2 minus square root of minus 5 gamma, plus 9 times, where does the 9 come from? Is the product of 2 plus square root of minus 5 times 2 minus square root of minus 5. That's 9 times delta. And that's equal to 2 minus square root of minus 5. Okay, so what's true here? 3 divides this first term in the sum, and 3 divides this next term in the sum. So you could use the distributive law in this ring to factor out a 3 and say 3 times 2 minus square root of minus 5 gamma plus 3 delta is equal to 2 minus square root of minus 5. So what's the point? 2 minus square root of minus 5 is now a multiple of 3 in this ring. So there have to be integers, a and b and z, so that 3 times a plus b squared of negative 5, which is 3a plus 3b squared of negative 5, is 2 minus square root of negative 5. And that's just not possible, right? There's no integer solutions where like 3a is equal to 2 and 3b is equal to negative 1. So this is a contradiction, and that means that I, in fact, is not the whole ring, that I is a proper ideal in this ring. All right, so now let's suppose that I is a principal ideal. And again, we're going to find a contradiction. Okay, so we'll suppose I is a principal ideal. Let's pick a generator for it. Let's say I is generated by a plus b square root of negative 5. So that means everything in I is something times a plus b square root of negative 5. So in particular, there exist alpha and beta in R with 3 equals alpha times a plus b square root of negative 5, and 2 plus square root of negative 5 equals beta times a plus b square root of negative 5. So if this ideal is generated by a plus b square root of negative 5, that means that both generators of this ideal that we were given, 3 and 2 plus square root of negative 5, these are two things that are in the ideal. So that means that they're both equal to something times this generator. All right, so we have this first equation. And if these are equal in z adjoint square root of negative 5, if we apply this norm function to both sides, we'll get the same thing. So on the left-hand side, we get 9. And on the right-hand side, we get norm of alpha times norm of a plus b square root of negative 5. Remember, the norm function is multiplicative. So what does that mean? Well, 9 is equal to a product of these two things that are positive integers. So what are the possibilities for a squared plus 5b squared? Well, it has to be some positive integer dividing 9. So it's either 1, or it's 3, or it's 9. So I'm going to pause and erase, and we'll see that each one of these cases leads to a problem. That no matter which one we try, we're going to get a contradiction somewhere. And in fact, that will show that I was not a principal ideal, that there's no choice of A and B that makes this work. Let's finish this proof that I is not a principal ideal. Where were we? We're down to 3 cases. A squared plus 5b squared has to be either 1, 3, or 9. Okay, let's suppose that it's 9. That means that norm of alpha is 1. And if you think about what norm of alpha equals 1 means, the norm of like x plus y times the square root of -5 is x squared plus 5y squared. So the only way that that could be 1 is if y is 0 and x is plus or minus 1. That is, alpha is equal to plus or minus 1. This is actually one instance of a more general fact that we proved last quarter about units in these quadratic integer rings, z adjoins square root of d, when d is a negative integer that is 2 or 3 mod 4. Sorry, when, yeah. Okay, well, anyway, so if a squared plus 5b squared is 9, that means norm of alpha is 1, so alpha equals plus or minus 1. So a plus b squared minus 5 is plus or minus 3. So what if it was 3? Then you would have 2 plus square root of minus 5 equals 3 beta, where beta was an element in z adjoins square root of -5. And there's just, that is not possible, right? Because you would get 3 times the first coefficient plus 3 times the second coefficient times square root of -5. And 2 and 1 are not divisible by 3. So if this is 3, you have a problem. If this is -3, you have a problem. Either way, a plus b square root of -5 being plus or minus 3 is not compatible with the second equation. Okay, what if it was 3? Well, if a squared plus 5b squared was equal to 3, well, it can't be equal to 3 because this equation, a squared plus 5b squared equals 3, just has no integer solutions. B would have to be 0 because otherwise you get something that's at least 5. And that means that a squared equals 3 and there are no integer solutions to that equation. So we're down to one case. What if a squared plus 5b squared is equal to 1? Well, that means that a plus b square root of -5 is equal to either plus 1 or minus 1. And in that case, what is the ideal generated by a plus b squared root of -5? Well, it is the ideal generated by 1 or minus 1, so it's the whole ring. So how do we know I is not equal to the whole ring? That's why we proved I is a proper ideal at the beginning of this argument. So it's always nice to look at your ideal and try to figure out, like, what does this ideal look like? Is it equal to the whole ring? But this is the place where we actually need the fact that I is not equal to the whole ring. Okay, so what have we seen? Not possible for a squared plus 5b squared to be 1 or 3 or 9. So it's just not possible for this ideal to be principal. So that means R is not a Euclidean domain. Because R is not a PID, R is not a Euclidean domain. And just a word of caution, we worked quite extensively with the norm in this ring that comes from the field norm. But we're not proving only that R is not a Euclidean domain with respect to this choice of norm. We're seeing that I is not a PID. Sorry, that I is not principal. So R is not a PID. So that means not only is R not a Euclidean domain with respect to this norm, but R is not a Euclidean domain with respect to any norm.